Good morning or afternoon, grade 11s. Depends on when you're looking at this. All right, really important lesson today. And I promised you yesterday that there would be a way to solve triangle problems, especially non-right angle triangle problems. This is like our big focus, because those are the more difficult ones to solve, and they can be very difficult to draw as well. So I'm going to teach you this method called the component method, and I'm telling you right now, it is a lifesaver in difficult vector problems, okay? So first I have to teach you what components are, and I made a very detailed note for you, and you can read it if you want. What components do when you're doing questions involving vector addition and subtraction and stuff like that, what they allow you to do is you can boil every problem down into one right angle triangle. Now, having said that, if the problem that you're working on is already just a right angle triangle, then really this method doesn't really help you, okay? But those are easy. Now, the ones that have, like, you're adding many off-axis vectors together and you don't get right angle triangles, this method is a godsend. Like, it really works great, okay? So it's made to, its method is specifically designed to help you with difficult problems, okay? The easy ones, which are already right angle triangles, I'm assuming you don't need any help with those, okay? All right then, so let's get right to it. First of all, what is a component? Well, here, let me give you an example, and you can read this for yourself too. I wanted to give you the video just to paraphrase it for you. But anyway, take a look at this. This vector here called vector A, okay, and I'm highlighting it with a rainbow for you. Let's call that vector A. Vector A is off axis, right? Like, it's not on the XY axis. It's off the axis, and there's an angle theta here that measures the angle between vector A and the X axis. So that's what I mean by off axis. It's not directly on the axis. Now, what we're going to do is we're going to project the vector onto the axis, okay? And the way we do that is we construct a right angle triangle, okay? And the two sides of the right angle triangle will be on the axis, and those two things will add up to give me my rainbow vector, okay? So if you look at this vector, the A vector, has a component along the x-axis that's this long, okay? It's sort of like the shadow that it casts onto the x-axis, my rainbow vector. Now, it has a y component that is this long, okay? So that's how, if you want to think of it as north, south, east, west, the red vector is how far east you're going. The blue vector is how far north you're going, if you want to think of it that way, okay? So this rainbow vector is the actual vector, and the red and blue vector are the components, okay? They're the components of A. Okay, so here, this is the, now let me write it with black. This is the X component, and this is the Y component. Now, I hope that makes sense to you, what I'm saying these components are. Like, basically, if you walked along this rainbow line here, you walk so many meters and you're walking on a line that's so many degrees north of east, well, that's the equivalent of walking this far east, this red vector here. Oh, I don't want to color it rainbow. This red vector here, that far east, and then this far north with the blue vector, okay? So if you get the idea, the components are the projection of the vector onto the two axes, and every time we break a vector into components, we're constructing a right angle triangle, okay? And that's a critical point, okay? Now, because this triangle is right angle triangle, the Pythagorean theorem applies, okay? So we know, for example, that the tan of theta would equal the y component here. That's the tan of theta down here. Would be the y component divided by the x component. Let me use the highlighter. So we know that that's true. That's SOHCAHTOA, okay? And we also know that the Pythagorean theorem holds true. In other words, the rainbow vector in size would equal the square of the other two sides added together. That's just the Pythagorean theorem. Now, one thing I'd like to point out also is, in order to find how big the x component is, you use SOHCAHTOA. So we use cosine of theta. Here, like, let me write it for you. If I wrote cos of theta, we know cos of theta would equal adjacent divided by hypotenuse, right? That's what you've learned in grade 10. Well, here, the adjacent side is AX. So this is equal to AX divided by the hypotenuse, and the hypotenuse is the original vector A. That's this vector here. And so therefore, if I solve the equation for AX, I get A times cos of theta. Now that's what this little thing up here is trying to tell you. Now, what are these absolute value signs next to it? That just means the size of the vectors. That'll give you the size of vector AX, okay, like the magnitude of the vector. Now, of course, AY similarly goes with sine because the sine of theta would equal opposite over hypotenuse, right? You learned that in grade 10. Well, in this case, that's equal to AY over A. And so therefore, AY equals A sine theta. Now, this is really sort of an important point with components. We're always going to use cos and sine to find our components, okay? Like if you're given a vector. And that's what's written here for the y component. You use a sine of theta, okay? So anyway, that's components. Really simple, right? We take a vector that's not on the axis, that's off axis, and we project it onto the axis. We create two components, okay? So like a vector that's north of east is so far east and so far north. We could do it for any direction. If it was south of west, we could say the two components are this far south and this far west, right? And basically, that's all there is to components. Very straightforward, right? Now, okay, so moving on, let's do an example. So here's an example of a vector, and now we're gonna use our cardinal coordinate system. So not x and y anymore, but north, east, right, west, and south. That's called the cardinal coordinate system. Okay, north, south, east, west, like on a compass. Now this vector that you see here is 120 kilometers, 30 degrees north of east. Now I've actually spelled it out for you here. 120 kilometers, 30 degrees north of east. So we're going to construct the picture here, and I'll use the rainbow color. That 120 is my hypotenuse, right? So here's my hypotenuse. That's the original vector. But like in the diagram above, I'll try to use the same colors. That corresponds to a certain distance east and a certain distance north, okay? So how far east are we going here? Well, because we know that cosine of theta would equal the east component divided by 120, we can find the east component, and I know I've written this somewhere else, but I'm just going to write it here for you because you're watching this video trying to summarize. This east component is going to equal my original vector times the cos of 30, and the north component will be the original vector, which is 120, times the sine of 30. Now we can actually work out what these numbers are. So you take out a calculator, punch in, 120 times 30 cos, and I get 103.92, so that's 103.92 kilometers. Okay, the original one is in kilometers, so that hasn't changed. This one works out to 60 kilometers. Okay, so if I'm like going 120 kilometers along the rainbow up here, going 120 kilometers along this rainbow line, 30 degrees north of east, you could get to the same spot by traveling 103 kilometers east, and then turning and going 60 kilometers north will take you to the same destination, okay? So these are the east and north components, okay? So the east one we colored red, and the north one we colored blue. The east and north components of the original displacement vector. All right, so that's components, right? Now, we can see, okay, like here I explained where the components come from, so we've got that. Okay, now there's a trick. What we want to do is we don't want to constantly have to draw that picture to get the components, okay? So when you get a vector like this one here, delta D is, whoops, sorry, I meant to highlight that. this vector here, where it says delta D is 580 kilometers, 22 degrees west of south. We want to know, like, without drawing a picture, because drawing a picture wastes time. Like the promise of this method, everyone, okay, the promise of this method is that you don't have to draw a diagram. So what if we could find the components without drawing a picture? Well, that would save us lots of time. So here's a little trick, a little pro trick for you. When it's written like this, 580 kilometers, 22 degrees west of south, one of those components, the west or the south one, will go with sine and the other one goes with cos. Well, the pro trick is this: whatever comes immediately after the angle and before the of, in this case it's west, so whatever's in that spot right there will always go with sine, whatever the direction is, whether it's north, south, east, or west. Whatever's in the second position after the of, that's this spot here, will always go with cos. And this is always the hypotenuse of your triangle, right? And so in order to find the west component, I know I don't want to draw the picture. It's going to be 580 times the sine of 22, which is 217.3 kilometers. To get the south component, it's going to be 580 times cos, okay, of 30, which is 502.3 kilometers. And there you go. I've broken my vector up into two components without even drawing a picture, okay? And that's what you want to do. You want to avoid having to constantly draw pictures, because otherwise you're wasting time. Okay, so once you've convinced yourself you understand what components are, then don't draw pictures. Like just sine and cos if you're asked for the two components. Okay. All right. Now there's some practice problems here. Okay, find the x and y components of each of the following vectors. So let me do a couple of these with you because there's a lot of questions here. All right, so we're going to use, I've been using red and blue, so I'll stick with that same color scheme. So here, 12 meters, and that's like 30 degrees north of east, right? But these are x and y now. It doesn't really matter what the coordinate system is, whether it's Cartesian, which is x and y, or cardinal, which is north, south, east, west. We do it the same way. So these are my two components. That one's going to go with sine because it's opposite, and this one's going to go with cos because it's adjacent. And so I don't even want you to plug this into your calculator. You don't need to. I just want you to see if you can figure out what the two components are. This is the hypotenuse. Okay. Oh, that's interesting. There. So that's the hypotenuse. So you're going to go, in order to get the x component, which is the red vector, you're going to go the hypotenuse. Whoa, this is weird. Maybe it's like acting up. Okay. You're going to go the hypotenuse, which is 12, and it's going to be times the cos of 30 degrees. And the y component is going to be 12 times the sine of 30 degrees. Good so far, right? Okay, now what about this vector here? The next one. Okay, well, the next one, the hypotenuse is 25. My x component is going to go here. I always get a right angle triangle, right? So my y component is going to go like that. There's my right angle between the two components. Okay, and then the angle is 60 degrees. So again, the x component in this case will go with cos. So it's going to be, the hypotenuse is 25 times the cos of 60, right? And 25 times the sine of 60. Makes sense, right? Now, what if you get this obtuse angle? Okay, this 150 degrees. Well, what you want to do is figure out the related acute angle that's closest to the axis. So what your question is, here, let me use a different color. I'll use orange. What is this angle here that I've colored orange? We'll call that theta, okay? Well, you know that theta and 150 have to add up to 180. So this is this is 30 degrees here. So I'm just going to write therefore theta equals 30 degrees. And then we have our two components. So there's one component like this, which is going in the, say, the west direction. The other one's going north like that. And I know theta is 30. I worked it out. So now I can write my two components. The x component, I think what this worksheet wants you to do is treat this side as negative and this side as positive. So we're going to write negative, okay, because it's pointing in the negative direction on the x-axis. And so we're going to write negative 15, which is the hypotenuse, times the cos of 30. That's how big the red vector is. It's in the negative direction. Remember, they're still vectors, right? They still have direction, and the north one is in the positive direction, the north one. So it's going to be 15 sine of 30. See, no problem, right? I did the first line for you, okay? Now, what they want you to do in line number 2 is actually take two vectors and add them together, okay? And this is the magic of the component method, guys. Let's say I wanted you to add these two vectors, okay? Just add them up. Well, you can draw a triangle, but it's actually very difficult to get that one correct. It's not a right angle triangle, but the beauty of the component method, you don't have to draw the triangles at all. Look, here's one of our components. Let's do the first vector first here. There's the other component. And then this guy here has an x component about that big, and the y component is this big, like that. So now watch this magic, okay? When I do the x component here, I'm going to get 12 times the cos of 20. And x2 over here is going to be 12 times the cos of 70. Now the y component is 12 times the sine of 20 here. And here this is 12 times the sine of 70. Okay. Now here's the thing. When you're adding them up, you can get a total in the x direction. So here we just add up these two numbers, like this one plus that one equals this one. Now these vectors are along the same straight line, so we don't need to draw a triangle. We don't need to use sine and cosine law. We don't need to use the Pythagorean theorem. We can just add those numbers straight up with a calculator. Okay, so watch. I'm going to do that right now. And I'm going to get 12 times 70 cos plus 12 times 20 cos equals, I get 15.38. So here I'm going to put 15.38 meters per second is the unit. Notice the units here. It's not just meters. You can add velocities this way. You can add anything you want. Okay. Now that's 15.38 meters per second. Now I'm going to get the total y component. I'm going to go 12 times 20 sine, okay, plus 12 times 70 sine, and I get 15. Did I do that right? 12 times 20. Pardon me for a second. I just want to verify that I got exactly the same answer. That's 12 times 70 goes equals 15.38. Now I get 12 times 20 sine plus 12 times 70 sine. Yeah, you get exactly the same number. All right, well, 15.38 meters per second. So here, what I did was I added these up. And it's just a coincidence that we get the same thing. So now they want us to put the vector together here. So here, we're going to go 15.38 this way on that component. And then we're going to go 15.38 in the y direction like this, 15.38, like that. And so my resultant vector is going to be a vector that looks like this. Okay, here's my rainbow vector. Let me zoom in on this here for a second. This vector is the sum of the other two vectors. Okay, so that vector there is the sum of the other two, and it's we constructed a right angle triangle. So you can use the Pythagorean theorem to work out the hypotenuse. Okay, you do it like a squared plus b squared equals c squared, right? So I'm going to square that number plus, and I get here, I'm going to erase this word sum. Whoops, I'm going to erase the whole thing. Just that part of it. Oh, I'll just draw my guy again, okay? Goes like that. So here, when I use Pythagorean theorem, I get 21.75 meters per second. That's how big that is, okay, using the Pythagorean theorem, right? In other words, using c squared equals a squared plus b squared, okay, and taking the square root. And now to find the direction of it, I'll go tan of theta equals 15.38 divided by 15.38. and I'm going to get theta equals 45 degrees. Don't you love this rainbow color? Okay, so that's 45 degrees. So this is 45 degrees here. See, so what I've done is I've constructed the answer. And all I did was add the components of each component can add with the corresponding component of the other vector, okay? Now, I want you to try doing the last line on your own. So I've done most of that page for you. Now, if you look at this page, page 3, okay, there are some other questions like this. So let's do some of this together. Can you write down the components, okay, of these vectors? So let's take a look at the first one. Okay, so the first one here, you're going this far east. You're going that far north. Okay, so what is the north component? Well, just write down what it's going to be. It's going to be 20 times the sine of 30, because the blue vector goes with sine because it's opposite the angle, and this one goes with cos. Okay, now the east one is going to be 20 cos 30. So this looks very similar to the last worksheet, just more practice. Okay, now this one here is interesting. I like this one. What is the west component of this vector? Well, the west component is like this. And then the south component is like this. But if you look at the question carefully, it's asking us for the north component. So south is negative north. So they're saying north is positive. That's what they're saying. But they're also saying west is positive. So the west one is a positive number. So let's do that one first. It's going to be 15 times the cos of 20, because this is adjacent, so it goes with cos. This is opposite, so it goes with sine. Here I'm going to write negative 15 times the sine of 20. Now the reason why I wrote negative is because they asked for north, okay? But this vector is not north, it's south. And south, if north is positive, that means south is negative here. North is positive here, okay? All right, so yeah, like pay careful attention to what they're saying here. Now this is a velocity this time, so they're asking you for the west component and the north component. That's pretty straightforward. The west component is that way, so west is positive. The north component is like this. That one will go with cos because it's adjacent to, oh, actually, careful now. I made a mistake. I just realized where the angle was. I got to be careful. All right, so now look, the angle is measured on the north axis. So this is the north component, and then the west component is like that. Now, in this particular example, that goes with cos because it's the north component goes with cos because it's adjacent to my 60 degrees. See that? And this one goes with sine because it's opposite my 60 degrees. So here, the west component is going to be 32, which is the hypotenuse right there, 32 times the sine of 60, okay? And the north component is 32 times the cos of 60. Some students get it in their head that the north one always goes with sine and the west one always goes with cos. That's not true. This example shows you, this one here, shows that that's not always true, okay? So sometimes it does, sometimes it doesn't. It depends on where the angle is being measured. All right, now this, I'm going to show you how to do these confusing ones down here where it says like 110 degrees. What you need to do is find the angle that's to the nearest axis, okay? So what's that angle there? Well, just go 110 minus 90. So 110, take away 90 degrees is 20 degrees. And then you just go ahead and do your west component of this acceleration. Any vector can be broken into components, so it's showing you different kinds of vectors. And the north component, but use 20 degrees, okay? That's it. All right, now in the second question, it says for each of the following, write the components. Well, just take note here that the first one after the angle always goes with sine, and that one always goes with cos. So the south component of this vector would be 35, which is, this one's the hypotenuse, okay? 35 times the sine, whoops, times the sine of 30. And the east component is going to be 35 times the cos of 30. That's how big the east component is. And here, okay, the west, this time west is going to go with sine, and that one goes with cos. Now, look carefully here. The west component is going to be, this is the hypotenuse here, 5.6 is going to be 5.6 times the sine of 15, okay? Now, they don't ask us for north, they ask us for south. So they're saying south is positive. Therefore, the north component will be negative 5.6 times the cos of 15. Okay, north still goes with cos, but they're asking for to treat south as positive, and so we have to treat north as negative. All right, I'll let you do the last one. Okay, now this question here is very interesting. What if I give you the components and ask you to find the original vector? So it's doing the opposite of question 2. See, in question 2 here, you give the original vector, which is this thing here, and what you do is you break it into 2 components. Well, what if we give you the 2 components and ask you to put them together? Well, this is easy because we know they make a right angle triangle. So here's the little trick. To assemble our components, just go like this. Delta D squared would equal 25 squared plus 12 squared. That's the Pythagorean theorem. But these make a right angle triangle. They always do. Okay, now I'm going to actually work out what the number is since I'm doing this one for you. So I'm going to go 25 squared plus 12 squared equals 769 square root. I get 27.7 meters is the unit. I stick with the same unit. Now to get the direction, here's the trick. Go for the direction, I'll write it underneath so I don't want to run out of room. Go tan of theta and go small over big. Okay, small, like look at this, over big. Okay, so which one of the 2 components is smaller? Well, it's the east component is small, but the north component, which I'll circle with a rainbow here, the north component is big. So I'm going to put small over big. I'm going to put 12 over 25. And I'm just going to take note that the top one is east. The bottom one is north. Now watch this. When I do the inverse tan, so I take my calculator, I go 12 divided by 25 equals 0.48. I go inverse tan, I get 25.6 degrees. So therefore theta, I'll just do it over here. Theta is 25.6 degrees, but then you're going to write east of north. You see this here? Whatever's on top of whatever's on the bottom. See, and I don't have to draw the picture to get it. That's the beauty of it. So now I'm going to write the answer. 27.7 meters, put a square bracket, 25.6 degrees. Whoops, that's not right. Square bracket, 25.6 degrees east of north. Whatever's on top, the smaller of the 2, of whatever's on the bottom. So in this case, it's east of north. All right, there you go. Now, by the way, if you have a negative component, like if you look at this vector, it's negative here, you have to change it to positive, okay? So I'm going to write, therefore, the east, because west here is negative, that must mean east is positive. So I'm going to write east equals 10.2 meters per second. And now I'll work with that number and I will ignore the negative 10.2. Okay, you see you have to do that here also. This means north is positive because the south, okay, the south that's in the picture, not in the picture, but in the variable. Okay, both of these are actually opposite. You have to change this one too. So we're going to make north and west positive. Okay. All right, so there you go. Now, I have some other problems for you to solve here. I'm going to let you finish the rest of those. Okay. Now, look at this. Okay. Question number 3 here. Now, I know that the numbers make no sense, but I just pulled these off of old assignments and stuff. So it says here, a bird travels 2.3 kilometers east and then 4.5 kilometers south. The trip takes 30 minutes, which is, you're not going to use 30 minutes. You're going to use 0.5 hours. It's half an hour, right? Now it says find the average velocity. Well, here, this makes a right triangle, okay? So just go ahead and draw the right triangle. It's easier. It's already broken into components for you. You just have to put them together, okay? And then divide by time. Pardon me, it's past my bedtime. All right, so now look at question 4 for a second, okay? Now question 4, interesting question. Okay, it says, what is the resultant displacement? And if you look, there are 3 displacements. Here's the first one, 100 meters, like the first one's 50 meters north. The second one is 100 meters, 30 degrees west of north, so we'll call it delta D2. And then here, delta D3 is 80 meters, 60 degrees west of south. Okay, so how do we get the total displacement when we have 3 vectors to add? And I want to show you the method, okay? Adding 3 plus vectors. Now it works with 2 or more, doesn't matter. I mean, you have to add vectors, okay? And they're all off axis, or in this case, one of them is on axis. The first one is on axis and the other 2 are off axis. Doesn't matter. When you're adding them like this, here's your method. 1, you make a table. And in the table, you have to decide what directions you're going to make positive. You have 2 decisions to make. Okay, so let's take a look at this. The first vector is north. Whoops. The first vector is north. Okay. The second one has north in it. And the third one is south. So we need to make a decision. What direction is positive, north or south? And it really doesn't matter what you choose, arbitrary choice. I'm going to make, since I have 2 norths, I'm going to make north positive, okay? Now I also have to decide about east and west because that's a totally different thing. Well, the first one's just north, okay? So it's not even, you know, it's not even east. There's no east or west in it. Pardon me, I'm getting tired. The second one is west. So we see that there's a west here. Whoops, I drew a little thing on. Okay, so we see that there's a west. The third one is also west. So we might as well make west positive because why would we bother writing down a bunch of negative numbers? Okay, so I make a little table, and then what I do is I take each vector and I put it in the table. Okay, so the first one is 50 meters north. So I'm going to write in my table 50 and 0. If I'm going 50 meters north, I'm only going north. I'm not going west. So that's my first displacement, 50 north, 0 west. Now I look at my second one, and I recognize that the west one's going to go with sine, the north one's going to go with cos, and the hypotenuse is 100, okay? So what I'm going to write in the second table, I'm not going to take out a calculator. The north one is going to be 100 times the cos of 30. So I'm going to 100 cos 30 and 100 sine 30. Okay, so that's my second vector taken care of. Now my third vector is 80 meters and it's 60 degrees west of south. So because we made north positive, that one has to be negative. So let's take care of that right away. This one's going to be negative 80 cos 60. And then the other component is going to be 80. It is west, so it's going to be 80 sine 60. Okay, now what I've done is I've broken the vectors up into components, right? Whoops, didn't mean to erase that. I meant to make it a little shorter. Okay, now our goal here is to find the resultant displacement, which means the total. So what do we do next? Well, number 2 is because we're trying to find the total, that's exactly what we're going to do, but we're going to find the total north component, And we're going to add these three together. This one plus this one plus that one. We're going to add those three together. So it's going to be 50 plus 100 cos 30 minus, and I'm sorry I'm running out of room, minus 80 cos 60. Okay. Now I get a total. So let's go ahead and do that. Okay, so it's going to be 50 plus 100 times 30 cos, and then minus 80 times 30 times, times 60 sine equals, and I get 67.3. I hope that's right because I kind of messed up my calculator there. Anyway, 67.3. Okay, and that's my north component. Now this, I'm going to add these together, and I get the total west. I just have to add them straight. So it's going to be 100 times the sine of 30, 100 times 30 sine plus 80 times 60 sine equals 119.28. So here I'm going to write 119.28. Okay, so now this is the magic of it. We had to add these three vectors. Two of them are off axis. We're not even using a diagram, but look what we did. Okay, now this number here is the north component of my answer, this number, and this is the west component of it. Well, all we have to do is put them together. This is a right angle triangle now. See, like the promise of this method is it turns hard problems into right angle triangles, right? So now I don't have to draw the picture. I'm going to write that the total displacement, therefore, squared will equal 67.3. This is Pythagorean Theorem plus 119.28 squared, right? So now let me do that. And I will just square 119.28 plus 67.3. Like I said, I hope that number's right. Equals that. Take the square root. I get 136.95. So I'm going to write 136.96. 136.96. Is it kilometers? They're all meters. Okay, so that's going to be in meters. And to get the direction of the vector, I'm going to do tan of theta equals small over big. Okay, so tan of theta is small over big. That one is small. Okay, my north component is small. My west component is big. Okay, so what I do is I'm going to write here my tan of theta. I'm going to write this is equal to 67.3 divided by 119.28. And what I did, I'm just going to take note. I put the north one on top, the west one on the bottom. So when I find my answer, it's going to be north of west. Okay. So what I do is I take 67.3, I divide it by 119.28, take inverse tan, I get 29.4 degrees. So theta equals 29.4 degrees, okay, north of west. So therefore my answer for the total displacement is 136.96 meters, and it's 29.4 degrees north of west. Okay. Now, I never once drew a diagram and I got the answer. Now, some students will be a little confused at first, but it's a simple method, okay? So step one, whoops, I didn't mean to draw that. Step one, okay, make the table. Write down the components of each vector in the table. Step two, add each component separately, the north ones, the west ones, okay? Step three, Pythagorean theorem. So let me write that as a 3. Pythagorean theorem to get the result, the size of the vector. And then tan of theta equals small over big to get the direction of your answer. And then we got that here. And that's it, you're done. 3 steps. Each step is actually really simple, okay? And we've turned a very hard problem to do any other way, really, into a pretty easy, just a right angle triangle, right? Okay, so I'm gonna let you work on the rest of this. Now that I've done some examples, you've got very little homework to do. There's actually, I think, almost nothing in your textbook on this. I'm gonna give you more practice later, but you've got a, actually, no, you guys at home, you don't have the quiz. You wrote the quiz already. I'm just remembering that. All right, so there will be more homework that I will post additionally, okay, to this because it's not enough, okay, by itself. So component method, you'll notice here in the homework, there are just worksheets that go with it. I'm gonna ask you, please, let me erase this nothing here. So I'm gonna ask you, please, okay, to not do these questions just yet, these ones here. Not just yet, okay? Save it for after the next lesson. Okay, because we didn't do this topic yet, relative velocity. So be careful. You have done this homework. So I'm going to ask you here, I'm going to write it down. Don't do this yet. So I gave you a few questions on the worksheet. I'm going to add some questions to it though. So when you look at this tomorrow, go to the page in OneNote. So go to where it says vector components, notes and practice. You will see some practice. There's a couple of other practice questions that we didn't do, but I did a lot of them for you. So why don't I give you some more practice, okay? And you can repeat, you can do the questions, more questions you can do on your own. All right, so guys, that's it. So that's the component method. Like I said, if you found any of this confusing, go back, slow down the, pause the video, look back at the sections, okay? And hopefully that you'll find that helpful. And that's it. So guys, have a good day and I will see you tomorrow.